It's a quick video explaining some radiation we'll be dealing with nuclear chemistry and what their symbols are. First one is alpha radiation. Alpha is a helium nucleus that comes out of a nucleus of an atom. We represent that as He 4/2. Beta is an electron that either gets captured by a nucleus or released by a nucleus, and its symbol is E 0/-1. Again, atomic mass over atomic number. You'll see why it's -1 later. Gamma is just high energy electromagnetic radiation that comes out, and it's given the symbol like a different looking Y. A positron is a positive electron. That's the antimatter for an electron, so it's the opposite charge. And its symbol is 0/1, and an E. And again, this one's electron capture. So you can have electron being captured by a nucleus or an electron given up by a nucleus. I want to just briefly describe, what this radiation is and how it impacts the nucleus. First of all, let's remind ourselves of atomic masses and atomic numbers. On the periodic table, each of the atomic masses are listed as decimals. Carbon is 12.01. Okay, and remember that's a weighted atomic mass averages of all the isotopes. And of course, the atomic number, here is 6. So if I was to represent carbon, I would represent carbon as C, and then round the atomic mass of 12, and then put it over its atomic number. So we always take the rounded atomic mass to the nearest whole number and put it on top, and then we put the atomic number on the bottom. Sodium, for instance, sodium, I'm going to round that to be 23/11. Now remember, the isotopes do exist for these, but the atomic masses are weighted atomic mass averages that we've already been dealing with before. All right, so let's talk about the nucleus of an atom and how it gets involved with nuclear reactions and things like that. So if this is a nucleus of an atom, the red spheres here represent the protons, and of course they're positive in charge. And the blue ones represent neutrons, and they are 0 in charge. For a nuclear reaction, we can either put a nucleus plus another nucleus together in fusion, and that's what makes a nucleus larger, or we can break it apart and take things out of it, and that's fission. Most things that we're going to be looking at in this chapter are going to be nuclear decay, which are fission. So what if I take a helium nucleus out of this and make it come out of there? Remember, we're going to represent that as He, and it's going to be 4/2. And that's +2 radiation. We dealt with alpha particles with Rutherford when he shot alpha particles from a natural radioactive source at gold foil, and some bounced off, a lot of them went through. We talked about that when we looked at the discovery of the atom. But the atomic mass is going to be 4. Atomic number is 2 for helium. What does that look like? So here's our alpha over here. This is He 4/2. Notice how there's 2 protons that came out and 2 neutrons, because this is what a helium nucleus looks like, +2. So if we take 2 of these out, and 2 of these out of the nucleus, this particle comes out as alpha. Now, when you break apart the nucleus, you release lots of energy, so these particles come off going pretty quickly. So I'll draw an arrow, meaning this is going to fly off here with a pretty high velocity. So that's what alpha radiation is all about. Now, before we deal, with any other nuclear reaction, I want us to consider, for instance, what a proton and a neutron is actually made out of. Before we do that, let's remember electron spin. We talked about electrons having an arrow up or an arrow down, and maybe, and this is a quantum effect. So if an electron is spinning in this direction, let's say it's got a magnetic moment up, and if it spins in this direction, it's got a magnetic moment down. But remember, that's really a relativistic effect that we interpret as electron spin. So we have up arrows and down arrows for electrons. Well, it turns out there are quarks that make up protons that have an up nature to them and a down nature to them. If they have an up nature, they have a +2/3 charge with them. If they have a down nature, they have a -1/3 nature of their charge. So there are three quarks that we want to talk about that make up protons and neutrons. And remember, there are other quarks out there. We're just looking at ups and downs. Okay, so this is a proton. Right now it has a plus charge, a +1 charge. How is that so? Well, it's got 2 ups and 1 down. So let's do that. We have an arrow up, an arrow down for its 3 quarks. So this is a +2/3 and a +2/3 and then a -1/3. When I take 2/3 plus 2/3 minus 1/3, I get a net +1. So the 3 quarks we're looking at, we got 2 ups and 1 down. That's what makes up a proton. Now again, there's other subatomic particles and other quarks. We're not going to deal with those, okay? So what if we change this one, okay, to a down quark? Well, then we have an arrow up and then 2 arrow downs, okay? And you're going to see then that we've got a +2/3 and then a -1/3 and a -1/3. And that adds up to be 0. So what we can do is we can take a proton and change one of its quarks to a down, and we can make that neutron out of this proton then. And then we're going to say that a positron, okay, came out of that. So we're going to go E, 0, and 1. So if we make a proton become a neutron, we're going to say a positron came out. Or we can say beta capture occurred. An electron would be 0 over -1 E. And this, of course, is our -1, and this is a +1. Okay, so anytime we have interconversions between protons and neutrons, the electron is involved. You can get beta capture, beta emission, or you can get positron emission. Okay, and we're interconverting protons and neutrons. And of course, anytime we do that, we indeed are changing the actual nature of the nucleus. So those are the main types of radiation I wanted to talk about today. Was proton conversion back and forth between neutrons with the electron or positron, and then the alpha particle. Okay, we're going to be looking at some nuclear reactions, but one of my favorites to talk about is carbon-14. So we're learning how to balance carbon-14 and other types of nuclear reactions. So carbon-14 does go by beta emission. So I'm going to write an electron here, 0 over -1. So again, electron beta is the same thing. And we want to figure out what particle, okay, is produced because of this. Well, the way we balance nuclear reactions is we have to remember that the sum of atomic masses on the top and the sum of atomic numbers on the bottom have to be equal on both sides. So we have 14 on the left side, that's all we got. And over here we've got a 0. So I got to think, what plus 0 gives me 14? Well, that's obviously 14. Okay, now over here I've got a -1 and I've got a 6. So I've got to make this side equal to 6. So I got to think to myself, what -1 would give me 6? So that's got to be a 7. So you see now 7 minus 1 is 6, and that of course is just 6 over there. So then I need to go to the periodic table and look up the atomic number of 7 on the periodic table and figure out what element it is. We don't want to pay attention to atomic mass, because remember, atomic mass is not what defines an element. We talked about that with the periodic table, and remember, the atomic masses also involve isotopes. There are different isotopes of elements. So if you look up a number 7 on the periodic table, you will indeed find that it is nitrogen. So now what do? Well, we have converted a neutron into a proton here. So we've had 6 protons before and 8 neutrons here. Now we have 7 neutrons and 7 protons. And I'll write that down for you, because 14 minus 6 is 8 neutrons and 6 protons, because we know that the atomic number equals the number of protons. Now over here we have 7 protons, and 14 minus 7 is 7 neutrons. And see how the beta emission, okay, has come out of this. Okay, so we've taken, it used to be 2 down quarks and 1 up quark. We've made 1 down quark now go to be up quark, making a proton. So that's kind of how these nuclear reactions happen. Okay, now let's go take a look at that worksheet, okay, that I want us to work on. Just a couple more examples here for us, okay? So here we go. our job now is just to kind of fill in the gaps here and balance these reactions. So if you look up sodium on the periodic table, you'll find that its atomic number is 11. So I'm going to write 11 here. And over here, positron is 0 over 1. If you look at the actual radiation chart that I gave you. And I can scroll back to that really quickly to make sure that you can see where that comes from. Okay, so positron is 0 over 1 here. Okay, and don't be afraid of the beta symbol. Okay, because there's times we'll say beta here instead of an E. Beta and E, these are synonymous with each other. Okay, so now we have to make sure the sum of atomic numbers equal each other. So there's 11 on this side, and 1 plus what gives me 11? So that must be a 10 here. Okay, all right, now looking at it, it looks like there's a mistake on this particular worksheet that I copied. This actually should be a 23. Okay, because 23 plus 0 gives me 23, and that should be 23. Okay, so what do we have here then? Well, if we look up number 10 on the periodic table, you'll find that that's the element neon. Now remember, don't pay attention to the 23. You'll notice that the atomic mass listed on the periodic table for neon is closer to 20. Don't pay attention to that, as this one is a particular isotope, okay, of that neon. So remember, the atomic masses can vary from the periodic table, but the atomic numbers won't. All right, so next. All right, so I've got another reaction here. This is tritium, hydrogen, 3 over 1. If you look at the atomic number for hydrogen on the periodic table, it's definitely 1. Okay. Over here, we have some kind of particle being added to this. This is some kind of form of electron. We know that this is going to be a 0 because electrons are all 0. And 3 plus 0 definitely equals 3. So we conserve the atomic masses. Looking at the periodic table, okay, we indeed have a 2 here for helium. Helium's atomic number is 2 on the periodic table. Okay, so you got to think, what should this be? Well, I know that 1 plus 1 is equal to 2. So this one has to be a positron. Okay, and hopefully that, again, makes some sense. So we're just, balancing the chemical reactions or nuclear reactions based on the sum of atomic masses and numbers. Okay. Well, we can do one more here, I suppose. So let's do letter C. So hydrogen, 1, we know that's a 1 here on the bottom because that's hydrogen's atomic number. We know carbon is 6. Okay, over here we have 1 plus 6 equals 7. Well, they already told us it's nitrogen, so we know that has to be a 7 because 1 plus 7 equals 7. And then 14 plus 1 is 15, so over here this has to be 15. So that's how we balance nuclear reactions, pretty easy. And the rest of this brief unit that we're going to do, we'll look at more kinds of reactions.